Picture this. You unplug from the internet on a plane, in a clinic with no signal, at a kitchen table with the Wi-Fi off. You type a question, and a genuinely capable AI answers. No account, no monthly bill, no token meter ticking, and nothing you typed ever left the machine. A year ago, that sounded impossible. The best AI lived inside enormous data centers, behind a login and a credit card. So how did a model that normally needs a rack of expensive server chips end up running on the computer you already own? The answer is genuinely clever. Let us open it up. The tool most people reach for is called Ollama, and the first thing to understand is what Ollama is not. It is not an AI model. Ollama is a runner. Think of it as the ignition and dashboard of a car. You turn the key with one command and it does the rest. It downloads an open-weight model, stores it on your disk, sets up how the model is prompted, and serves it on your own machine, offline if you want. It is free, open source, and runs on a Mac, a Windows PC, or a Linux box. So hold on to the split. Ollama is the driver. The model is the thing it drives. And the engine doing the heavy math sits under the hood, which is where the real magic is. So why want this when you could just open a chatbot in your browser? 3 timeless reasons. Privacy. Your prompts and documents never leave your device, so nothing is sent off to be stored or trained on. A doctor can keep patient notes right on the machine in front of them. Offline. It keeps working with the network unplugged on a ship, in a remote clinic, anywhere the internet is missing or expensive. And cost. Once it is downloaded, there is no bill, nothing metered per question. And this is no toy version. You can run a whole library of serious open-weight models, families like Llama, Q-Wen, Gemma, DeepSeek, and Mistral. Some are tuned for chat, some for code, some for reasoning, some are multimodal and can look at an image. You pick one that fits your memory. And it serves a standard programming interface right on your computer, so developers can build search tools, coding assistants, and document readers on top of it, without a byte leaving the machine. Now for the part that actually matters. What is an AI model physically? Here is the honest answer. A model is a giant list of numbers. That is it. These numbers have a name you should know. They are called the parameters, or the weights. When you hear a model described as 7B, that means roughly 7 billion of these weights, 7 billion numbers tuned during training. All of the model's knowledge lives inside those numbers. And running the model, the step the field calls inference, just means doing arithmetic with those weights over your input again and again to predict the next chunk of text. So a model is its weights. Hold on to that because the whole trick depends on it. Here is the problem this whole story exists to solve. Each of those weights is by default stored as a 16-bit number, which is 2 bytes of memory for every single weight. So do the arithmetic on our 7 billion weight model. 7 billion weights times 2 bytes each is roughly 14 gigabytes, just to hold the numbers, before the model does a moment of real work. That is more than a lot of laptops have free, and far more than a typical consumer graphics card can hold. So at full size, the model simply does not fit. This is the wall, and the way over it is the most important idea in this video. The idea is called quantization, and it is beautifully simple. If each weight costs 16 bits, what if you stored each one in fewer bits? Take it from 16 down to 8, or even down to 4. At 4 bits, that same 7 billion weight model drops from about 14 gigabytes to roughly 4. Suddenly it fits in an ordinary laptop. Now here is the single most important correction in this whole subject, so listen closely. Quantization does not delete any weights. It does not remove neurons, cut out layers, or shrink the model's brain. The model still has exactly 7 billion weights, the same count as before. You have only changed how precisely each one is stored. Same number of weights, fewer bits each. Say that to yourself. It is the line most explanations get wrong. But there is no free lunch. When you store a number in fewer bits, you have to round it onto a coarser set of options. At 4 bits, every weight has only 16 possible values to land on. Picture a smooth color gradient forced into just 16 steps, close to the original but not exact, and those tiny rounding errors are sprinkled across billions of weights. So quantization is really a dial. At roughly 8 bits, the model is nearly identical to the original at about half the size. At roughly 4 bits, you hit the common sweet spot, a big shrink with quality loss that is usually almost invisible. Push down to 2 bits and it gets clearly worse. Higher number, more bits, bigger and better. Lower number, smaller and faster but rougher. And the wonderful part is that this dial is yours to set. You might reasonably ask, how does cutting a number down to 4 bits not wreck the model? The answer is a clever scheme, and you will see its name everywhere. Weights are not rounded one at a time in isolation. They are quantized in blocks. Each block shares a single scale factor, a multiplier that stretches the coarse 4-bit codes back out to roughly where the real values were. The modern version, called K-quants, goes further, nesting small blocks inside bigger ones and spending more bits on the weights that matter most. That is why a label like Q4KM holds onto most of the model's quality at about a quarter of the size. And that label is just shorthand. Q for quantized, 4 for 4-bit, K for the K-quant scheme, M for medium. Once you can read it, the whole zoo of model files stops looking like noise. So the model has been shrunk. Where does it all get packed? Into a single file format with an odd name, GGUF. And right away, let us correct something because the internet gets this wrong constantly. You will see GGUF expanded as GPT-Generated Unified Format. That is a myth. It has nothing to do with GPT. GGUF stands for GGML Universal File, and the GG comes from the name of the engine's creator, Georgy Jurganov. What makes this file clever is that it is self-contained. It holds the quantized weights, plus the model's blueprint, its settings, and crucially the tokenizer, the part that knows how to chop your text into pieces. One file, everything inside, nothing else needed to run it. It is even designed so the computer can map it straight into memory and pull in only the parts it needs, so a big model loads fast. So who actually does the math? That is the engine under the hood, and the foundational one to know is called llama.cpp, built by that same creator on a math library called GGML. Its whole purpose is to run this inference on ordinary hardware with almost no setup, adapting to whatever you have, plain laptop processors, Apple's chips, NVIDIA and AMD graphics cards. And here is a neat trick. A model is built in stacked layers. If your graphics card can only hold some of them, the engine puts as many layers as fit onto the fast chip and runs the rest on the regular processor. That hybrid split is how a model slightly too big for your card still runs. One honest note. Ollama started on top of llama.cpp, but it now also ships its own engine for newer models, both built on that same GGML core. So it is not true that every model goes through llama.cpp, though the same engine family powers them all. Now here is the catch almost every guide leaves out, and it is what separates really understanding this from just following steps. Getting the weights to fit is not the end of the story. While the model reads and writes, it needs working memory called the KV cache. To avoid redoing the same calculations on every word, it stores a little packet of memory for each token it has seen, across the whole conversation. And here is the trap. That cache grows as your prompt gets longer. With a short question, it is tiny. But feed the model a very long document, and that cache can swell until it rivals, or even dwarfs, the weights themselves. A small 4 GB model fed an enormous prompt can quietly demand tens of gigabytes more and grind to a halt. So never assume that if the weights fit, you are done. The length of what you ask is its own memory cost. So how does running AI on your own machine stack up against big cloud services like ChatGPT, Claude, or Gemini? It is a genuine trade with no clean winner. Local gives you privacy, offline use, zero cost, and a model that is truly yours, but it is bounded by your hardware, so you usually run a smaller model. The cloud gives you the very largest frontier models, always fast, no setup, but your data leaves your device, you pay per use, and a company controls it. The local software itself is free and open source. No token meter, no subscription. The only real price is the machine you already own and a little electricity, and the true gatekeeper is memory. Your model's quantized size, plus that growing context cache, has to fit inside your RAM or graphics memory. There is also, for honesty, an optional paid cloud tier for giant models you cannot fit at home, but that is a side door. Now name the honest gap. The strongest open-weight models have nearly caught the best closed ones on knowledge and coding, but the models winning those benchmarks are huge, hundreds of billions of parameters, and do not fit on a laptop. What you run at home is a smaller cousin, so expect a gap that is real but narrowing, never that local cannot keep up. It clearly can. And one last caveat, these models are open-weight, the numbers are downloadable, but that is not the same as fully open source. Different models carry different licenses, some with real restrictions, so check before you build a business on one. Let us clear up the things people get wrong because they are everywhere. 1. Quantization shrinks the model's brain. No, it keeps every single weight, it just stores each one in fewer bits. Same count, lower precision. 2. GGUF means GPT-Generated Unified Format. No. It is GGML Universal File named for Georgy Jurganov, nothing to do with GPT. 3. Ollama is the AI. No. Ollama is the runner, the model is the GGUF file, and the math is done by the engine underneath. 4. Running locally means running ChatGPT or Claude on your laptop. No, those are closed. Locally you run open-weight models like Llama or QN, usually a smaller one. And 5. If the model file fits in my memory, I am set. No. The context cache grows with the conversation and can blow past the weights. Get these 5 right, and you understand this better than most articles written about it. So step back and look at the shape of all this. For years, real AI capability lived locked inside data centers, behind a login and someone else's servers. Quantization plus a free runner quietly changed that. A genuinely capable model now fits on hardware you own, processing data that never leaves your hands. That is a kind of personal AI sovereignty, AI as a private utility instead of a rented service. And the trend underneath is the real headline. Every year, the model that needed a data center last year fits on a laptop this year. Models get smaller and smarter, quantization gets better, and the line of what runs locally keeps chasing the frontier, even as the frontier keeps moving up. So the real question was never, can AI run on my own computer? You just watched exactly how it does. The better question is this. Now that it can, what do you want it to do in a place where no one else can see it?